in the least amount of damages. We're also using machine learning to identify substitutes for products. So typically, product pairs that are frequently co-viewed but rarely co-purchased are good candidates for substitutes. We show our customers low-price substitutes and also show substitutes to customers when a product that they may be looking for is out of stock. Amazon, of course, has been a pioneer in the area of product recommendations. We proposed collaborative filtering algorithms way back in the 1990s. Most of you have probably seen on the Amazon product page the widget customers who bought this also bought. And this widget is powered by highly scalable data mining algorithms. We're also using machine learning for ranking search results and surfacing the most relevant results to users and customers. Now, moving on to the seller side, we're using machine learning to forecast the future demand for each product. Now, these demand forecasts need to be extremely accurate because if you forecast the demand to be too high, you're going to be stuck with excess inventory, and if you forecast the demand to be too low, then the product could go out of stock, and this would lead to a poor customer experience. We're using machine learning also to improve the quality of our product catalog. Now, a key challenge here is classifying hundreds of millions of products that we have in our product catalog into our product taxonomy, which has over 50,000 leaf nodes. So this is a massive multi-class classification problem. When multiple sellers on our marketplace list the same product, we end up with duplicates in our catalog. Identifying and eliminating duplicate products from our catalog is critical for many applications. So for example, in search, we don't want to show duplicate products in search results. It wouldn't lead to a great customer experience. And now if you look at the bottom here, we're actually applying machine learning techniques to diverse types of data: text, images, speech. On the text side, we're using named entity recognition techniques to extract attributes from product titles. We have a visual search app that allows users to point their phones to a product and retrieve visually similar images from our product catalog. And for this particular application, we need to learn image representations that capture the notion of visual similarity. In other words, images that are visually similar have to have representations that are close. And of course, all of you have heard, or maybe many of you also own Alexa. In Alexa, we use parallel implementations of deep learning models to do voice recognition, to understand customer intent, and also carry out conversations with users. So lots of applications of machine learning across many different domains within Amazon. Literally, machine learning is powering many of the products and services that we offer from Amazon. So in this talk, I'm going to dive deeper into details of two specific applications. One is question answering, and the other is catalog quality. Okay, both are very important applications for Amazon. So let's look at question answering. Now, Amazon product pages contain a wealth of information. We have product descriptions that contain information about product specifications like camera megapixels on a phone or battery life of a phone, while customer reviews shown here capture user feedback and sentiment about different product features. We even have community QA data that contains authoritative answers to customer asked questions. These are typically open-ended questions that people ask about the experience that users have with a product or how a product compares to other products. Now, the average product page for the top 20 best-selling products across categories contains about 4,000 keywords, right? So you can imagine that finding information is difficult, especially with smartphones. So to make it easy for users to find information that's embedded in product descriptions, customer reviews, community QA, we have implemented a question answering interface on our product pages. Here we've shown a screenshot of the text interface for users to ask product questions. And this is the box here where a user can type in their question. Okay. Now, majority of questions, product questions, are about product features. For example, for like camera megapixels or battery life and so on. Now, these can have factoid answers that can be directly extracted from product descriptions. So, for example, the question here is how heavy is it? And this has a factoid answer, 8.6 ounces, right? These type of questions can have more subjective answers that are available in product reviews. So, for example, the question here is this expensive? And this has the following answer, which is for the price, this is good value for money for an amateur photographer, right? Now, observe that the snippets that contain the answers for these two questions do not have high text overlap or high text similarity scores with the questions. Here, you had the keyword heavy in the question, but you have item weight as the are the keywords in the snippet, and there's no overlap between these words. Similarly, here you have expensive as the word in the question, and value for money as the phrase in the snippet, and there's no overlap between them. So what this implies is that we need to perform semantic matching between questions and snippets. So let's see how we go about doing that, right? Now, before that, there's another popular category of questions which are product similarity questions that compare two products with each other. So, for example, here, again, there's a question that is how does this model compare with another model, right? And there's an answer in the community QA that answers this question. Similarly, we have, another popular category of questions is product compatibility questions, which is how well a pair of products work well together, right? And here again, there's a question here, and the product description has a snippet that contains the answer to the question. Now, a key challenge in question answering is really understanding the semantics of questions, right? So, for example, the question, what is ISO, refers to the definition of ISO, but the question, what is the ISO, refers to the ISO value of the camera. So just the word the completely changes the semantics of the question, and this is something that we want to understand. As we saw earlier, we need to perform semantic matching between questions and snippets, since there may be very few overlapping words between the question and matching snippets containing the answer. And this is because customer questions and review snippets can refer to a product attribute like price in several different ways. Bang for the buck, cheap, inexpensive. These are all valid ways of referring to price. And matching these different variations of meanings requires semantic matching. Of course, you want to give natural language answers. For the question, is this expensive? A possible answer could be, this is great value for money, right? And now, also in order to ensure superior customer experience, we do want to answer questions with a high degree of precision. Our question answering system that we have deployed in production operates at more than 90% precision. As we saw earlier, again, users may ask a wide range of questions. The data required to answer some of these questions may not be available in product descriptions or reviews on the product page. So, for example, here's a question, will this suitcase fit in the overhead of an airplane? You may not have the data to answer this question on your product page. It could require to know, knowing what the dimensions of the overhead in an airplane is, and that also varies, between different airplanes and so on. And finally, the data that's contained in product descriptions or reviews that we use to derive answers may not be accurate, and this could lead to incorrect answers, right? So to find semantically matching snippets for a user question, we we learn joint embeddings of questions and answers so that semantically related questions and snippets have embeddings that are close by. Now, embeddings are nothing but mappings to a higher dimensional vector space. So we learn these embeddings using Siamese neural networks that are trained on question, relevant snippet, irrelevant snippet triples. These training examples, which comprise of triples, are generated from our community QA data. So we take question answer pairs as the question and relevant snippet, and we randomly select a third snippet. And there are some other ways of cleverly selecting the negative or the irrelevant snippet triple. Now, we show these here. There is an example. The question is it expensive? The relevant snippet here is good for the price, for the given price, and then an irrelevant snippet to the question is autofocus is great, right? And now word embeddings of the question, relevant snippet, and irrelevant snippet are input into three separate recursive neural networks that generate sentence embeddings for each of them, and that's shown here. These word embeddings down here are generated, are computed using Word2Vec. Most of you probably have heard of Word2Vec. It finds vector representations of words based on contextual similarity. And then the question embedding is combined with each snippet embedding in an additional layer at the top here that outputs either the probability that the snippet is relevant to the question. This is modeled by a logistic function applied to the dot product of the embeddings, or that the layer outputs the cosine similarity between the two embeddings, the question and the snippet embedding, right? Now, we consider several different loss functions. I think some stuff is getting equations, maybe, I don't know, some text is disappearing, but that's fine. Now, we consider several different loss functions that we minimize in order to learn the embeddings for questions and snippets so that questions are embedded close to relevant snippets. The first loss function is log loss or cross entropy loss. It's the negative log of the product of probabilities of the relevant and irrelevant snippets. The second loss function shown here is Siamese loss. It is the standard loss function for Siamese architectures that was proposed by Wang et al. In their 2014 CVPR paper. So if you look at this loss function, it tries to maximize the margin between the cosine similarity scores of the question with respect to relevant and irrelevant snippet, right? So the loss function imposes a penalty if the difference between these cosine similarity scores drops below threshold m. But once the difference exceeds m, the loss function value drops to 0, right? And there were some other loss functions that we have also proposed. The performance metric that we use in order to evaluate these different loss functions is precision at rank 1. So this is essentially precision at rank 1 measures the fraction of times that the snippet with the closest embedding to the question embedding is relevant, right? And our baseline here, again, I think the slides have gotten distorted a bit, but the baseline here is standard cosine similarity between question and snippet text. Now, you can see in the table, actually the numbers are a little bit occluded here, but the baseline, which is the simple text matching based on cosine similarity, has a pretty low precision at rank 1, it's somewhere in the mid-50s. But if you look at our semantic matching approach, which is learns these embeddings using loss functions, the precision at rank 1 metric is much higher, somewhere in the 90s, okay, 96%. The other thing to notice here is that Siamese loss, which maximizes the margin between these cosine similarity scores, has a much higher precision at rank 1 score compared to log loss, which minimizes the negative log likelihood of the data. So the choice of loss function is extremely important. So that's one major takeaway. The second major takeaway from this slide. The first takeaway would be that semantic matching gets you much better results than simple text matching in terms of precision numbers. So here are some qualitative results for our for our question answering system. As you can see, a question answering system returns semantically matching snippets for the first 4 questions. It figures out that basketball in the first question is semantically related to the word sports in the matching snippet that it has returned. Similarly, in the second question, which is around price, it figures that price and costs are semantically related. Semantic matching snippet for how big is it contains the word item dimensions. And in the fourth question, stabilization and blurry are matched semantically by the question answering system. Of course, there are areas where our system doesn't work as well. So for example, this question here, how much weight can it hold? So this is a tripod, a question about a tripod, camera tripod, about the weight that it can hold, and our question answering system answers that the weight of the tripod is 2.2 pounds. So clearly, I think there's still some ways to go to handle some types of questions, but many of the questions we're able to get pretty good semantic matches. Now, moving on to the second part of my talk, which is on catalog quality. Now, the Amazon product catalog in India has close to 200 million products, and our catalog contains fairly rich metadata about products, a number of attributes like title, descriptions, images, and so on. And it's very important for us to ensure that the information contained in these different product attributes is factually correct. The information between these attributes is consistent, and also that the information that is contained in the attributes adheres to pre-specified guidelines. Now, since sellers are responsible for populating this metadata, the product metadata on our marketplace, some of the product listings end up having defects. Now, these poor quality product listings erode customer trust, they hurt sales and conversions of products, and they also lead to excessive returns on our platform. So it's very important to fix these defects, and we use machine learning techniques to identify and fix defects, catalog defects at scale. So let me talk a little bit about some of the examples of defects in our catalog. This slide shows examples of title defects, right? So for example, in this first product listing, the title is extremely long, and it has all sorts of spam keywords: Bollywood, designer, beautiful, latest design, and so on. So these are superfluous words, and presumably sellers have put these words in to gain more impressions, to be shown as part of search results, and so on. The second product listing here has this email in the product title, right, which is again spam. Here there are a few examples of defects with product images, so for example, in this product image, it doesn't really adhere to our pre-specified guideline that the background should be white, right? And there are all sorts of other objects in the background that are distracting. Ideally, we just want the product on a white background. Similarly here, this product image is sort of cropped and does not show the complete product. So these are all product image defects that we'd like to eliminate or suppress in our catalog. This slide shows defects involving mismatches between product attributes like titles and images. So for example, here the title says that this product is a t-shirt, but the product image shows a bag. Similarly, here the title says it's a blue dress, and the product image shows a pink dress. Now, if a user were to place an order for this dress, I don't think they'd know whether they're going to end up getting a pink dress or a blue dress. And they're just not going to place an order. Or they're going to place an order and get something that they didn't want and return the product, both of which are not very desirable outcomes. Now, key capability to identify and fix such defects is the ability to extract attributes from, especially like brand, color, size, model, from product titles and descriptions from these text attributes. So for example, in this title here, Dustin is the brand, transparent black is the color. And we use deep neural networks to extract attributes from titles. The product title is input into a deep neural network with multiple layers. The embeddings generated by the bidirectional LSTM layer is input as features into the CRF layer that then generates these labels for the different words in the title. So for example, white gets labeled as color, Apple gets labeled as brand. Now, another key capability is the ability to detect image defects, extract image attributes such as color, and also classify images. So for example, we need the ability to predict that this image here has poor quality, this image here contains a product whose color is red, and this image contains a t-shirt. It belongs to the t-shirt category. Here again, we use deep convolutional neural networks that generate image representations that are then used input as features into ML models to perform the different classification tasks. And once we have extracted attributes like brand,